a powerful technique that, if applied carefully, can enhance your ALMA images and significantly improve their dynamic range. As we learned in our video on calibration, the Earth's atmosphere can introduce phase offsets and amplitude variations, often called gain fluctuations, to the astronomical signal before it reaches the telescope. These fluctuations can distort the wavefronts before they are detected, introducing errors in the visibilities and poor images. Gain fluctuations can be caused by clouds drifting over the observatory, by ice structures in the upper atmosphere, or by a number of other processes that change over timescales of seconds to hours. Interferometers like ALMA can correct for much of this distortion by calibrating the amplitudes and phases using observations taken every few minutes of bright point sources within a few degrees of the science target. Because a point source has no angular size and its position is well known, any phase shift or amplitude variation must be caused by the net atmospheric distortion. While standard gain calibration at ALMA yields very high quality data, it is not perfect. For example, the calibrator could be observed through a slightly different part of the atmosphere from the science target, or there could be phase variations caused by the atmosphere that occur more rapidly than the cadence at which the calibrator is observed. These residual phase variations will scatter flux from the science target into different parts of the image, increasing the noise in the image while decreasing the signal of your target. In other words, the final dynamic range, that is the ratio between the peak brightness and the RMS noise in the image, is often limited by residual calibration errors. If, however, the science target has some reasonably point-like structure and a high enough signal-to-noise ratio, it may be possible to use the science target itself to generate calibration solutions. This process is referred to as self-calibration and is the same as that used in standard gain calibration. But in this case, the calibration source is the science target. Typically, a self-calibration solution is derived using continuum observations and then applied to any spectral line observations as needed. Self-calibration is an iterative process that uses your source to better calibrate the antenna-based visibility amplitudes and phases as a function of time. During the self-calibration process, you build up a model of the source using an algorithm such as CLEAN and compare the model to the observations. This comparison is then used to derive the corrections needed to make the data resemble the model more closely by calculating phase and amplitude corrections. In practice, the process is as follows. First, create a model. This can be done by doing a very conservative clean of the image, meaning a shallow cleaning, including only the most believable emission. Then you compare the model to the data and derive corrections on a specified timescale called the solution interval. Next, you apply the corrections and reimage. As a final step of the first iteration, check to see if the dynamic range has improved. If the dynamic range has improved, then proceed to the next iteration, this time over a shorter solution interval and slightly deeper clean. Self-calibration can be continued as long as each iteration continues to provide an improved model or better time sampling of corrections to phase amplitude variations. Self-calibration should be stopped when the dynamic range no longer increases, if the target flux decreases, or if the image reaches the predicted thermal noise. Let's look a little more closely at solution intervals. These timescales are typically shorter than those on which the phase calibrator was observed in order to correct for calibration errors not already accounted for by the phase calibration process. Ideally, we like to use the shortest possible time interval for our calibration solutions. defined by the data sampling time of a few seconds. However, it's the signal to noise of the science target that sets the limit on the shortest feasible solution interval. In general, the best practice is to start with longer solution intervals, for example the length of a scan, and move to shorter intervals with each iteration. When choosing a solution interval, you want to balance sampling the variations in the solutions and maintaining an acceptable level of signal to noise in the solution. Each time you derive new solutions, you should view the solution table to see if most antennas are getting reasonable solutions. If a lot of the solutions are being flagged, typically this means you don't have enough signal to noise on that solution interval. Once this occurs, you've gone too far. Go back one step to the previous iteration and use that as the final dataset. Why not do self-calibration on all datasets then? The technique works best when there are compact sources in the data because the model we rely upon is most accurate for point sources. Accordingly, images with mostly extended structure will not provide good calibration solutions. Where compact structures exist, as we discussed before, you need to have sufficient signal to noise per solution interval in order to derive calibration solutions. As a rule of thumb, with 40 antennas, you should have a signal to noise ratio of at least 20 before self-calibrating your data. When self-calibration can be carried out, why bother then with regular phase calibration and not go straight to self-calibration? Remember that the sources used for phase calibration are both relatively bright and have accurately determined positions. Positions of science targets are usually not known to a great precision a priori, and regular phase calibrations are needed to calibrate science target positions as well. Finally, there are two types of self-calibration, as with any calibration process: phase self-calibration, as we've discussed in this video, and amplitude self-calibration. Amplitude self-calibration is less commonly used and is more prone to divergence. If amplitude self-calibration is performed, it should be done with extreme caution, only after several rounds of phase self-calibration, and the amplitude solutions should be checked carefully before applying them to the data. We've just taken a brief look at self-calibration, a powerful technique that can help to enhance your ALMA images. Be sure to check out our other videos. Happy imaging!